Hello, welcome to the second day of the machine learning course. My name is Said Al-Bohadani. I'm a postdoc in high-dimensional statistics and omics data integration. I'll be giving the lecture for the morning session. The morning session is about unsupervised learning, dimension reduction and data integration. The morning session consists of three parts. The first part is principal component analysis, PCA. The second part is partial least squares, PLS. And the third part is two-way orthogonal PLS, or O2 PLS. We will now start the first part, PCA. Suppose we have a dataset X with n rows and p columns. The dataset can be anything, for example, gene expression values, metabolite abundances, questionnaires, and so on. N here is the sample size, so the number of subjects, and p are the number of features, or the number of genes, metabolites, and so on. So here is an example of a dataset. We see the samples across the rows, so sample 1, 2, and 3, and we see the features across the columns, gene 1, gene 2, and so on. And we see that each gene and each sample has a measurement. The general question here is how to inspect these variables and their correlations. Which variables are important, or which samples are important, and so on. So let's give an example with bivariate data. Suppose we have two genes, gene 1 and gene 2. And these two genes are highly correlated. So here you can see a scatter plot of gene 1 against gene 2. So gene 1 is on the x-axis and gene 2 is on the y-axis. Here each dot represents a sample, and we have around 100 samples. We can see that they are highly correlated because they almost follow a straight line. So the question is, how would you represent these data? Do you really need both dimensions? So do you really need both gene 1 and gene 2? Or is one dimension enough? For example, a combination of the two genes. We can see that most information is contained in the direction of the straight line. This is also the direction where the variance is very large. Why? Because the spread goes from the lower left part here all the way to the upper right part here. Note that if we would take another direction, for example here, the spread would be very low rather than very high. So this direction along the straight line is composed of a part of gene 1 and a part of gene 2. This means that we don't need both directions. Simply let's say the average between gene 1 and gene 2 still represents this dataset well. And this is a general principle. For 2, 3, or high dimensional datasets, often you find that a combination of features is already enough to represent the data. For example, a combination of gene 1 and 2. In general, this combination can be found by looking at the direction of maximal variance. So we saw that the most interesting direction is the direction of maximal variance, especially with correlated data. To actually find and calculate this direction, we need a little bit of math. Again, X is our dataset, where each column has zero mean. A linear combination of X, of the genes, can be written as the product of the data matrix X and a so-called weight vector W. And this weight vector W is a vector with p numbers, so the number of features in X, and the resulting product, or the resulting projection, is or can be written as X times W. The dimension of this product is the number of samples times 1, because a vector has one column. Now, to calculate the variance of this product or projection, the sample variance of X times W, because each column has zero mean, you can more or less calculate it as the squared, or the square of X times W. However, because this is a vector, you need to work with the transpose. So the resulting sample variance is 1 over n, or 1 over n minus 1, times x times w, times x times w, with a transpose in between. And you can write it down as 1 over n, or n minus 1, times w transpose x w. So the message here is that for each w, for each combination, for each direction, we can calculate the variance of that direction. And subsequently, we can look at w that maximizes this variance. That's where PCA comes in. The optimization problem is as follows. So we want to maximize this sample variance of x times w over all w. However, we do require that the squared elements in w, so the sum of the squared weights, sum up to 1. Why is that? Well, that's actually an exercise later on. So this is something that you don't have to know, but to solve this maximization problem, we can apply the Lagrange method. The objective function is as follows. We maximize this sample variance minus lambda times the constraint, right? So the maximizer has to yield maximal variance and satisfy the constraint. So as with all maximization problems, you can try to first differentiate with respect to w, and then set the result to 0. Well, if you do that and you write it out, you get the following equation: x transpose x times w is equal to lambda times w. And this is actually a very popular equation in linear algebra because the resulting w that satisfies this equation and thus maximizes the variance is the first eigenvalue of x transpose x. So the resulting w is the first eigenvalue of x transpose x. Or equivalently, and that's computationally actually more attractive, we can say that the resulting w, the maximizer of the variance, is the first right singular vector of x. Right? So the first eigenvalue of x transpose x, or the first right singular vector of x. So this means that basically the first principal component, when you apply PCA to x, is the first eigenvector of x transpose x, or the first right singular vector of x. We can give an example in R to see how it works. So here I have two genes. Gene 1 consists of 4 measurements, -2, 0, 1, and 1. And gene 2 consists also of 4 measurements, -3.5, 1/2, 2, and 1. Note that they both have 0 mean. And if you plot gene 1 against gene 2, so here you can see gene 1 on the x-axis again, and gene 2 on the y-axis, you can see here the first measurement, first sample, -2, -3.5, and so on. You can see that they kind of follow a straight line, where one point is maybe a bit off, but that doesn't matter. So this data, these two genes are also highly correlated, or at least correlated. Now, how do you calculate the principal components of this data set? So first, the data set is given by the combination of gene 1 and gene 2. So you basically put gene 1 in the first column and gene 2 in the second column. And you can do that in R using cbind. So cbind gives you a matrix where gene 1 is the first column and gene 2 is the second column. Then you calculate the singular value decomposition. And that's in R, you can do that with the SVD function. And you specify that you want the right singular vectors. Right? Remember, the first right singular vector of x, which is this thing here, is the first principal component of x. If we do that, this is the resulting. These are the resulting right singular vectors. You can see that the best W is more or less 0.5, 0.87. So what can we say? The direction that maximizes the variance is 0.5 times gene 1 and 0.87 times gene 2. So why does gene 2 get a higher weight than gene 1? Well, if you look at the variance of the individual genes, we can see that gene 1 is, let's say, between -2 and 1, and gene 2 is, let's say, between -3.5 and 2. So gene 2 has a higher variance, and therefore gets a higher weight in the PCA decomposition. So how do you interpret the results, the components? First of all, the weights, W, are numbers for each feature, let's say each gene, indicating the importance for that principal component. So how important is gene 1 or gene 2 for that principal component? Now, if the weight is 0, that means that that gene is not important, and the higher the weight is, the more important. And note that these weights are relative. The squares sum up to 1. The result of projecting the data onto these weights are called scores. So the scores are constructed by taking this product x times w. Now the scores, you can say it's, let's say, a new representation of the samples in the direction, in the principal component direction. And these scores T, again, indicate the importance of each sample for that component. So the weights indicate importance for each feature, and the scores indicate importance of each sample. So to summarize, for a given dataset X, we want to inspect variables and their correlations. Based on a bivariate scatter plot, we find the direction of maximal variance. This direction of maximal variance is represented by weights for each feature. And these weights, to get this maximal variance, these weights are calculated by a singular value decomposition. And the first singular vector, the first right singular vector of X, is the first principal component of X. So these are that's for the weights. And then the projections of the data onto these weights are called scores. Right? So the scores are a representation of the data in the direction of maximal variance. And one can interpret or plot the weights and scores to understand which features or samples are most important. So if you plot the weights and you see one particular weight being very high, or one particular score being very high, you can track back which gene that was or which sample that was, and look further in your data to understand where this comes from. Or, for example, you can see a cluster of weights or a cluster of scores. Also here you can look at the genes in that cluster to see whether they are maybe biologically relevant together, or you can look at this cluster of samples, maybe you have some population stratification or some batch effect. Using PCA thus gives you ability to inspect the data set, both from the genes perspective and feature perspective, but also from the samples perspective. This was the first part of the morning session. Thank you.